Welcome to the channel Maths for Graduates. Today we are going to prove a theorem. Statement of this theorem is every monotonic function is Riemann integrable. Okay, so let's start. Suppose function fx is defined on closed interval ab, okay, and it is given that this function is monotonic, so it can be monotonic increasing or monotonic decreasing. Okay, we will prove this theorem by considering fx is monotonic increasing. Okay, we will consider that this function fx is monotonic increasing. Okay, but first let us do the partition of interval AB in such a manner such that its norm is less than delta. Now partition of AB is given by, suppose P is that partition and P equals to x0, x0 is A, x1, x2 and so on, xn is B. Okay, and norm of this partition is less than delta. Okay, so norm of P is less than delta. Okay, that means length of each subinterval will be less than this delta. Okay, hence del xi will be less than or equals to delta. Okay, since we have considered fx is monotonic increasing, hence f of x0, this will be less than equals to fx1 less than equals to fx2 less than equals to and so on fxn. Okay, now let us find upper Riemann sum UPF. Okay, so UPF will be UPF this equals to capital M1 delta x1 plus capital M2 delta x2 and so on capital Mn delta xn. Okay, here capital Mi's are supremo function in ith subinterval. Since fx is monotonic increasing, so supremo function fx in first interval will be fx1. Similarly, supremo function fx in second subinterval will be fx2 and so on. Okay, now putting the value of supremums, then UPF will be this equals to fx1 delta x1 plus fx2 delta x2 fxn delta xn. Okay, now let us find lower Riemann sum LPF. Okay, so LPF will be LPF this equals to small m1 del x1 plus small m2 del x2 and so on small mn del xn. Okay, and here small mi's are infimum of function in ith subinterval. Okay, and infimum of function in first interval will be fx0 and in second interval will be fx1 and so on. Now putting the value of infimum of function. Okay, so LPF will be this LPF equals to fx0 delta x1 plus fx1 delta x2 and so on fxn minus 1 delta xn. Okay, now suppose this equation is equation number 1 and this equation is equation number 2. Okay, so now subtracting equation number 1 and equation number 2. Okay, so on subtracting we have UPF minus LPF this equals to fx1 minus fx0 and taking common delta x1. Okay, plus fx2 minus fx1 into delta x2. Okay, and so on fxn minus xn minus 1 delta xn. Okay, since norm of partition is less than delta, so del xi will be less than delta. Okay, so replacing all the delta xi with delta. Okay, so when you replace del xi with delta, RHS will be greater. Okay, so UPF minus LPF, this will be less than equals to f x1 minus f x0 delta plus f x2 minus f x1 delta, and so on, f xn minus f xn minus 1 delta. Okay, so now taking common delta in RHS. Okay, so on taking common delta, we have f x1 minus f x0 plus f x2 minus f of x1, and so on, f xn minus f of xn minus 1 and into delta. Okay, so now you can see some terms are cancelling out. So cancelling those terms, fx1 cancel out, fx2 cancel out, and fxn minus 1 cancel out. Now we are left with f of xn minus f of x0 into delta. Okay, so now choosing epsilon such that this epsilon equals to f of xn minus f of x0 delta. Okay, so from this equation delta will be epsilon over f of xn minus f of x0. Okay, so now UPF minus LPF, we have UPF minus LPF, this is less than epsilon. Okay, so for this epsilon we have this delta. Okay, so now this fulfills the condition of Riemann integrability. Okay, hence fx is Riemann integrable. Okay, so this completes the proof that every monotonic function is Riemann integrable. Okay, so this video ends here. If you have really learned something from this video, then show support by subscribing the channel and also press the bell icon. Thank you. Thanks for watching.